In this video, we'll talk about the basis of a vector space, or a real vector space that we've been dealing with so far in this class, and how we can think about that in the dimension of a space based on what the basis is. So there's many different spanning sets for R2, which denotes our two-component real vectors. And if you go beyond just R2, any vector space has these properties. There's many different spanning sets for them. Now, for a spanning set, what I mean is that I can write every vector in this space R2 as a linear combination of things in the spanning set. Or, said a different way, if the span of that set is the whole space R2. So in this case, for this first set here, 1, 0, and 0, 1, the sort of standard basis, we'll get to that word in a second, for R2, we can see that any vector, A, B, we can write as A times the first vector 1, 0 plus B times the second vector 0, 1. If you do the same for any of these sets, I could do it here. It would involve solving a system to get to the coefficients, but the system's always going to be solvable. And the same goes for this one here. But this one's even easier. I can write any vector AB as A times 1 minus 1 plus A plus B times 0, 1. And if you work this out, you'll see when you combine those vectors, you get exactly AB. And these work for any real numbers A and B. They span all of R2. Now, what's a distinction among these spanning sets? Well, what you'll note importantly is that this last one here has 3 elements in it, while the first ones all have 2. And it seems kind of strange to have spanning sets with different numbers of elements in them, because you'd think if you're solving a system, you only need a certain number of equations every time to solve for the coefficients. So is there something we can use to distinguish these two? And the answer is yes, it's linear independence. If you work out the calculations, you will see that these first 3 here are all linearly independent sets, whereas the last one is not. That's the example we saw previously. The fact that if I take one of these and one of these, I get the middle vector here with 3, 2, just adding those other 2 ones up. So this last one is not linearly independent, while the other 3 are. So this idea leads us to a new definition, and that's the definition of a basis. So a basis of a vector space, you can just think, R2, R3, any number of n component vectors that you want here. And a basis is a linearly independent spanning set. There's 2 components here. There is linearly independent, and there is spanning set. So if I have a collection of vectors that I'm calling a basis, that means that both I can get everything by linear combinations of those ones in my set, and they are linearly independent, meaning they sort of don't overlap or sort of conflict. There's not too much information there. So just to sort of clarify about definitions here, a vector space is basically anything where I can add 2 things or multiply by constants, which are the exact 2 operations we can perform on normal real component vectors. I can add vectors together and I can scale them by constants, which means I can do linear combinations. Hence, all this stuff makes sense. A subspace is just a subset of a vector space that also has these operations that is closed under them, which means that if I take 2 vectors in there and add them, I stay in there. If I take a vector that's in the subspace and scale it, it stays in there. So it's closed under the operations. None of this here is super critical, but just so it's there, in case you picked up the words here, basically a basis means I'm taking whatever collection I have that obeys nice properties for vectors, and I'm finding a linearly independent spanning set of it. Now, what's the key here is dimension. So the dimension is the number of vectors in a basis for that space. And this number is uniquely determined by the vector space. The basis itself is not. There are many different bases for a given vector space. For example, we saw before for the space R2, we had one option as 1, 0, and 0, 1, and a second option as 1, minus 1, and 0, 1. Those are different sets, and they are both bases for R2 because they span R2 and they're linearly independent. The basis is not unique, but the dimension is because in both cases I have two vectors here. So our conclusion is the dimension of our two of these two component vectors is 2. Thank goodness. If all was right in the world, this dimension should have been 2, and it is, so we're happy about that. And similarly, you could say that the dimension of Rn is n, as it should be. N component vectors gives you n dimensions, which is great. So that's the idea of what a basis is and what the dimension of a vector space is, and we'll see examples of how this becomes important as we move on for the different types of problems we want to solve using linear algebra techniques.